Good evening, Blackpool. This is Gaia. Its 5-year mission was to map 1 billion stars. It did that so well, they decided to make it a 10-year mission to map 2 billion stars. So why map the stars in the Milky Way? How can they be mapped accurately? What data can you acquire, and what can we learn from all of the shed loads of data that are coming out of the Gaia mission? So let's start with why map the stars. As astronomers, we're used to the idea that we need to know where the things are in the sky, all the celestial objects, so we can find them again and see if anything has moved and see if any new objects have appeared. But Gaia is doing far more than that. It's determining the positions of stars to very high precision. And so with that information, we can gain a better understanding of the structure and the evolution, the history of the Milky Way itself. So how do we map the sky? Do we just take lots of pictures and stitch them together? Well, that works fine if you're mapping the Earth from satellite, for instance, but you can't do that with the sky because the stars move. I'm not talking about the apparent motion of the sky because of Earth's rotation. I mean all the stars are in motion. Nothing in the galaxy is static. And of course, a second problem is that all the stars are at different distances, so simply obtaining lots of two-dimensional pictures is not good enough. We need to know the three-dimensional positions of all the stars if we want to understand the structure of the Milky Way. You're familiar with this idea, I'm sure. If we look at, for instance, the constellation Orion, it might have a particular shape as seen from Earth, but all the stars are actually at different distances, so even stars that appear similar brightnesses may be very different. We need to know the distances. And bear in mind that we need to know distances not only to understand the structure of the Milky Way, which is a very important element of what Gaia is doing, but we actually need to know the distance to stars simply to understand the stars themselves. If you think of the Hertzsprung-Russell diagram, where we effectively classify stars according to their luminosity on the vertical scale and their surface temperature or colour on the horizontal scale, without knowing the distance to a star, we can't determine its luminosity. We can't tell if we're looking at a very bright star that's a long way away or a very dim star that's very close to us. So for instance, if we were looking at a blue star, well, are we looking at a blue supergiant or a main sequence star or a white dwarf? And similarly, if we're looking at a red star, are we looking at a supergiant, or are we looking at a red giant, or are we looking at a red dwarf? We can get some clues from the spectrum, but really, to understand the true luminosity of a star, we need to measure its apparent brightness and know its distance. And also bear in mind that if we don't know the type of star we're dealing with, then actually we don't know much about any of the planets that might be orbiting that star. Remember the techniques we use for looking at exoplanets, such as spectroscopic techniques, they tell us about the mass of an exoplanet relative to the mass of its host star. And similarly, the transit method tells us the size of an exoplanet relative to its host star. So if we don't know anything about the host star, then actually we don't really know much about the exoplanets. So knowing distance is absolutely critical, not only for understanding the Milky Way, but for understanding any of the stars within the Milky Way. And I guess you probably know, because a lot of astronomers are familiar with this idea, that if we want to know the distance to at least the closest stars to us, then we use a technique called parallax. We use the motion of the Earth around the Sun to look for apparent changes to the position of a nearby star, as indicated by this diagram on the right. And it's always said that parallax basically looks for the motion of a nearby star relative to a more distant star, the so-called fixed stars. And of course, the angle that we're interested in is that one shown on the right-hand side, the parallax angle. Bear in mind that this diagram is hugely exaggerated because the distances to the stars are perhaps millions of times larger than the distance from the Earth to the Sun. So although the movement of the Earth around the Sun does produce an apparent shift of the stars, those shifts are tiny. And also remember that this cartoon is misleading, because when we talk about the motion of a nearby star relative to a fixed star, well, there's no such thing as a fixed star. All of the stars in the Milky Way are in motion, and they all appear to move as the Earth orbits the Sun. In terms of distances, well, a hypothetical star at a distance of just over 3 light years would show a parallax angle of 1 arc second. And so we call this distance 1 parallax second. And 1 parsec is just over 3 light years. Of course, the nearest star is about 4 light years, so all stars will have a parallax angle of less than 1 arc second. And the much more distant stars, hundreds or thousands of light years away, will have absolutely tiny parallax angles. So there's the crux of the problem. To calculate distances, which is a crucial element of what we're doing, if we want distances, we need parallax. But parallax needs the star's actual positions on the sky. It's not good enough simply to measure the position of one star relative to another star, because all the stars are moving, partly because of the Earth's motion, and partly because the stars themselves are moving, the so-called proper motion. And all of these apparent motions and actual motions are tangled together, and we've got to separate them if we want to make sense of the three-dimensional structure of the Milky Way. That's why mapping the stars in the Milky Way is not a trivial task. That's why it's taken quite a while for the technology to catch up to the problem. We've known that we wanted to do this for many, many decades, but only recently have we had the technology that made it possible. So, how do we map the positions of the stars accurately enough to determine their absolute motions as well as their parallax and hence their distances? We need to be able to untangle these two. So we need very high precision measurements, and we need a fixed coordinate system. Remember, we need very high precision because the parallax angles are very small fractions of an arc second is what we're trying to get at. And we need a fixed coordinate system because the Earth is in motion around the Sun and the stars are in motion, so we can't use any of the stars as a fixed point in space. We need some other fixed coordinate system. Just as a little bit of an aside, back in the 1980s there were thoughts of, why don't we make this problem easier by making the parallax angles larger? Instead of having an Earth-Sun distance as the baseline of our triangle, why don't we send a spacecraft out to the outer reaches of the solar system? And there were plans to send a spacecraft out to 1000 AU. An AU being the distance from the Earth to the Sun, 1 astronomical unit. If you do this with an ion drive, it would have taken about 50 years to get there, bearing in mind that the Voyager spacecraft have only reached about 150 AU from Earth. So even if this plan had been started in the 1980s, it would still be on its way and wouldn't have arrived on station even now. But the plan was never actually put into practice. So, what coordinate system are we going to use to map the stars to this phenomenal precision that we need? You're familiar, I'm sure, with the equatorial coordinate system. That's right ascension and declination. They're analogous to the longitude and latitude on the Earth. They are effectively extensions of the Earth's equator and the Earth's pole, giving us a grid system that gives us right ascension, the analogy to longitude, and declination, analogous to latitude. RA and DEC have been used in star atlases since the days of the first Astronomer Royal, but they're not good enough. Why not? If we think of star atlases, we're used to the idea that we can look at the positions of any star and we can read off its right ascension and declination. And if we think of star atlases, here for instance we've got Norton's 1950 and Norton's 2000. These are not the publication dates of these star atlases, they are the epochs, the dates at which the coordinates of the stars are given. And that is because the coordinates are continuously changing. Remember, the coordinates are relative to the Earth, and the Earth's axis is precessing. And therefore, the coordinate of any object in the sky is going to continuously change day on day on day. Therefore, right ascension and declination are not suitable for the coordinates that we want. You might say, okay, if an Earth-based system is not suitable, what about using the Sun as a reference point? Well, even that would give rise to small errors because the Sun orbits around the solar system's centre of mass. This little cartoon shows it's moving over the last few decades, and the animation slows down a little bit as it approaches the near future, showing that the centre of the solar system is actually slightly inside the Sun, or will be in a few years' time. If we go back a few years, the Sun was quite a bit off-centre from the centre of the solar system. That's simply because Jupiter and Saturn happened to be on the same side of the solar system and, in a sense, were counterbalancing the Sun. So although we tend to think of the planets orbiting the Sun, well, actually they don't. The planets and the Sun all orbit around a common centre of gravity, which in astronomy is often called the barycenter rather than the centre of gravity or the centre of mass. And it's this that gives us the best fixed reference point. The best coordinate system that we can come up with is one that uses the centre of the solar system as a fixed reference point. So if we were to look at the sky in detail, if we imagine zooming into the sky, all of the stars that we can see will appear to move as the Earth moves around the Sun. For those stars that are very close to us, they'll appear to move in relatively large circles with large parallax angles. The more distant stars, those circles will be much smaller. If we take into account the actual motion of the stars as well, we'll get the parallax as well as a drift of the stars as the stars move around the centre of the Milky Way. So in effect, every star in the sky is corkscrewing through the sky. And we need to be able to measure that corkscrew as accurately as possible, because if we can measure the apparent motion of the star, then we can disentangle the circular or elliptical motion because of the Earth around the Sun, and that gives us the parallax angle, and that gives us the distance. We can separate that from what is essentially linear motion shown by the straight arrow of the star's motion around the Milky Way. The stars aren't necessarily travelling in straight lines, but over a period of a few years, compared to the rotation period of the Milky Way being 100 million years or more, it's essentially over a few years virtually a straight line. So if we can measure positions accurately enough, then we can disentangle actual motion from distance. The first satellite that tried to do this was called Hipparchus. There's the acronym at the top there. It was partly that acronym, and partly the name was a homage to the Greek astronomer Hipparchus, the founder of trigonometry. The Hipparchus satellite had the job of cataloguing 100,000 stars with a precision of order milliarc seconds. So 0.001 arc second, 1 milliarc second was its nominal precision. And it could look at something like 100,000 stars down to a magnitude of about magnitude 12. And when it was complete in the 1990s, it actually provided one of the first very high resolution catalogues that was used by the Hubble Space Telescope, so that the Hubble could make sure it was looking precisely where it thought it was looking. Gaia is the next generation of Hipparchus, if you like. The actual acronym, well, we don't have to worry about the acronym itself. GAIA originally stood for that, but it was originally thought that they were going to use an interferometer for measuring star positions. They actually changed the design of how Gaia was going to work, but they liked the name so much they decided to stick with the name regardless. Gaia's mission was to improve on the Hipparchus results by mapping not 100,000, but by mapping 1 billion stars, not to a precision of milliarc seconds, but to a precision of order 10 microarc seconds, where 1 microarc second is 1,000th of a milliarc second. Higher precision for the measurements means that you can measure smaller parallax angles, and that means you can measure distances to much more remote stars. And hence, effectively, the reach of Gaia was much larger than the reach of Hipparchus. And with the technology of the teenies rather than the 90s, it was able to go down to stars with magnitudes of order 20 rather than magnitudes of order 12. Let's just remind ourselves how ridiculously small these angles actually are. Here's an analogy that tells you about Gaia's ability to measure tiny angles precisely. Its nominal resolution, when the full data releases are available, it is hoped will be of order 10 microarc seconds. That's equivalent to the thickness of a human hair as seen from a distance of 1,000 kilometers. So imagine you're standing at Land's End and you're looking at an object at John O'Groats. You're determining the position of that object to a precision of the width of a human hair. That's the sort of angular precision that we're talking about with Gaia. You could ask, well, aren't any telescopes getting even close to this? Think about what we've got at the moment. For instance, we've got the Hubble Space Telescope, a superb instrument sitting above the atmosphere there, giving us very high resolution images. And we've got the Scimonyi Telescope, originally called the Large Synoptic Survey Telescope. If we think about whether or not these could do the job, well, certainly Hubble has got very high resolution, and certainly the Scimonyi Telescope is able to catalogue billions of stars. But unfortunately, they both can't do both. The Scimonyi Telescope doesn't have particularly good resolution, 100 times worse perhaps than the Hubble, and the Hubble has only managed to get the parallax of perhaps 1,000 or so stars. If you wanted to get 1 billion stars, well, the Scimonyi could do that in 10 years, but at rather low resolution. And if you wanted the Hubble to do its high resolution work, well, it would take probably more than 1,000 years, perhaps up to 5,000 years. And I don't think any of us really want to wait that long. So how does Gaia achieve its phenomenal resolution? Gaia is an ESA project. A lot of the components were made across Europe. The optical components, for instance, made in Belgium, France and elsewhere. The detector was from the UK. Some of the power subsystems were from the UK. And they were all brought together from across Europe and put together by the company called Astrium, which is now part of the Airbus consortium. It was constructed in the noughties and eventually launched in the early teenies, launched in December 2013 and placed into a halo orbit around L2 in January of 2014. Let's just remind ourselves about L2. There it is, sitting 1 million miles above midnight. There's the midnight point on Earth, the point opposite the Sun, and L2 is there 1 million miles above midnight. Sitting at L2, a sun shield can block the light from the Sun and the Earth and the Moon in just the same way that it does for the James Webb Space Telescope. So here is the sun shield itself being tested at Astrium. Just like James Webb, they tested it over and over and over again to make sure that it would deploy correctly. You can see solar panels on the back of the sun shield. That's how it gets its power. And it gives you an idea of the scale of Gaia. You can see it's a few meters in diameter, the sun shield about 10 meters or so in diameter. So you can ask, well, okay, Gaia isn't that large, so how does it achieve its microarc second precision? We know that large mirrors give higher precision, but it would need a mirror a few kilometers in size to give you 10 microarc second precision. And clearly Gaia doesn't have a mirror kilometers in size, given that it's only a few meters in diameter. If we remind ourselves about the scale of telescopes, here's the number of telescopes shown to scale. The largest telescope in the world at the moment is Gran Telescopio Canarias on La Palma. It'll be shortly overtaken by the extremely large telescope shown on the right there. But the space telescopes are shown in the bottom left. If I make those a little bit larger so you can see them a little more clearly, notice that Gaia, with rectangular mirrors, no larger than Kepler and certainly no larger than the Hubble Space Telescope, which has a circular mirror, or the various hexagonal segments of the James Webb Space Telescope, which collectively give us a mirror about 6 meters or so in diameter. So Gaia isn't that large, and yet it achieves very high precision. How does it do that? Well, it's an ingenious combination of the instrumental hardware that it employs and the way it is used, a novel mode of operation. So let's have a look at those. Firstly, hardware. It has a large detector, something like a gigapixel. So we've got about 1 billion pixels of a detector made up of over 100 individual CCDs. Each of those CCDs is a charge-coupled detector. We'll look at how they operate shortly. And I've said Gaia is a telescope, but actually Gaia is 2 telescopes. That's why it has 2 mirrors. These 2 telescopes point in different patches of the sky, and we'll see why shortly. Now for the novel mode of operating. Both telescopes create star images on the same detector array. You might think that's a bit crazy. Why would you have 2 telescopes and then generate images which go onto the same detector? Isn't that going to be really confusing? Well, actually, it's an integral part of the way that Gaia works. And the second novel mode of operating is that Gaia spins. And so the star images continuously drift across the detectors. Gaia does not take images. If it tried, it would just get lots of really blur images because it is continuously spinning. That makes Gaia very different to, for instance, imaging space telescopes that we're used to, like the Hubble or the James Webb Space Telescope. And it is how the data is pulled off the detector, the CCDs, that's a crucial difference between the way Gaia works and the way imaging telescopes like Hubble or James Webb work. So it's worth taking a moment to have a look at how we go from a detector. Remember, light is hitting the detector, light hits a CCD which generates charge, and the question is, how do we get that charge off the chip in order to generate the data that tells us this much light arrived at every pixel in the detector? It's going from physical hardware to the noughts and ones that tell us about the light that's arrived. That is what is fundamentally different between Gaia and the other space telescopes. So let's remind ourselves how CCDs normally work. When we've got a CCD in a telescope and we want to take an image of the sky, how does that work? Remember, we're trying to get the image data out of the CCD chip. Normally, CCDs work in what is called stare mode, which means you ask your telescope to stare at a patch of sky. With an amateur telescope, we might put the telescope on an equatorial mount so that we derotate the Earth and the telescope always points to the same chunk of sky. With a telescope like Hubble, its internal gyros stabilize it so it's always pointing at a particular patch of sky. The CCD is exposed to light, and slowly, over seconds or minutes or hours, the image slowly builds up. Once the exposure is complete, the data is read by shuffling all the pixels into a register, and then the register is read out 1 pixel at a time, and the amount of charge recorded in each pixel is recorded. And then the next line is shuffled down, and then the process repeats, pixel by pixel by pixel. It takes about a millisecond to shuffle all the data down, and it takes about a microsecond to shuffle the data across and read each pixel. Eventually, here I'm only showing a few dozen pixels. Of course, in practice, we're reading millions of pixels from each CCD. When we're done, we're left with an empty CCD. All the charge has been drained, and now we have a whole load of data that tells us how much light arrived at each pixel. Simply from knowing the order in which the data is read out, we can tell the order in which we can reconstruct the image. That is stare mode. Stare at the sky for as long as necessary and then read out all the data. Gaia doesn't work that way. Gaia works in so-called drift mode. The stars are continuously drifting across the CCD. And the trick is that the CCD is read out and shifts in synchronization with the drift of the stars across the CCD. So as the star drifts across the CCD is being read line by line by line and shuffled down, and the image is building up until the star reaches the edge of the CCD, at which point the register is read out, and when it finds a star, it makes a note of the time according to an onboard atomic clock. So it's not taking images, it's recording the time it takes for a particular star to reach a particular point in the detector. And that's going on not one star at a time, but it's going on in parallel for lots of stars across lots of CCDs. Let's return to this idea of why on earth are we using 2 telescopes but 1 detector? Well, there is a precedent for doing that, and you've probably heard of this instrument. It's called a sextant. You probably have one in the boot of your car, just in case you ever fail your GPS, and who knows, if you still need to get home, then a sextant is the way to do it. How does a sextant actually work? Well, basically, you have a couple of mirrors and you line up the horizon through a small telescope. And if you want to know the position of a star in the sky, or the sun perhaps, if you want to know the position of a star, you adjust mirrors until the star appears in the same line of sight as the horizon, because one of the mirrors is semi-silvered. This means that if you want to know the altitude of the star, you don't have to look at the horizon, look at the star, look at the horizon, look at the star. The two are brought together, and if you want to know the angle of the star, you simply have to read off the vernier scale at the bottom. So it's the angle of the star you want for navigation. But the reason I'm talking about a sextant is because it's the same principle as Gaia. Light from 2 objects is reflected from mirrors so that they appear together on the same detector. In the case of the sextant, the same detector means your eye. So the star and the horizon are both brought to the same point on the back of your eye. It doesn't matter if you're on a ship and there's a bit of a swell on the ocean and you're moving from side to side. That doesn't change the fact that the star and the horizon are fixed together by the angles of the mirrors in the sextant, which can be read very accurately. Even if you are moving backwards and forwards by quite a few degrees, you can get the altitude of the star very accurately. Same idea for Gaia, except that this time we're talking about 2 telescopes pointing in different directions. Telescope 1 and telescope 2. You can see the telescope mirrors are about a metre and a half by a half metre. We want much higher precision in one direction than the other, which is why the mirrors are rectangular. They're bolted onto this large odd-looking donut, which is the optical bench, which is designed to keep them precisely in position. There's the engineers at Astronomical putting it together. So let's have a think about this array of CCDs. A large number of those arrays are called astrometric CCDs. They are responsible for measuring the positions and ultimately the timings of when a star arrives at a particular point. Each of those CCDs has got the measurements as shown there, and each of the CCDs has about 9 million pixels, and each pixel is rectangular because, again, we want much higher precision in one direction, the horizontal direction, and we're not so interested in the resolution in the other direction. Before the star actually arrives at the astrometric CCDs, it goes through one of two sky mappers. These sky mappers are a collection of CCDs that are responsible for telling the onboard computer which telescope produced this star. In other words, it is effectively a bookkeeping exercise of this star came from telescope 1, so I'll make a note of that star as it drifts across the detector. Whereas this star came from telescope 2, I'll make a note of that as this star drifts across the detector. Once it's gone past the astrometrics, the light from the star goes through a couple of prisms to measure how blue is the star and how red is the star, to give us a crude measure of its colour. And for some of the stars it goes through a full spectroscope so that the full spectrum of the star can be taken. There's a few other chips in there responsible for instance, making sure everything is in perfect focus. And the star drift direction is from right to left as we're looking at it. And it takes about 4 seconds for a star to drift across one of the CCDs. So it takes about a minute for a star to drift across the entire detector as Gaia spins. Let's have a look at the operation. ESA have provided us with a nice video to give us an idea of how it actually works. The two telescopes are color-coded here, one magenta and one cyan, so it's easier to keep track of what it is we're looking at. Let's have a look at the cyan telescope first. Telescope number 1, the light is reflected multiple times so that a very long focal length is kept folded, and the light then hits the detector and produces a number of star images which will be moving from right to left. The other telescope, looking at a different chunk of sky, again folded to produce its set of stars, which again are mapped onto the same detector. As Gaia spins, all of the stars drift from right to left. Let's watch one star. As it is tracked across the detector, it gets brighter and brighter. Once it reaches the end, its brightness and the time is noted. And then for the next CCD, it gets brighter and brighter and brighter. And then the brightness and the time it reaches that point are noted. And that occurs again and again and again and again as a star drifts across the whole set. Then a measure of how blue is the star, how red is the star, and for some of the stars we'll then take a complete spectrum of that star. So that is the data that we're collecting. If we think about what's actually happening, this is not necessarily in real time, but it's a reminder that stars are drifting across CCDs all the time and are being read whenever they reach the end of any of those CCDs. In this cartoon, we have perhaps a couple of dozen stars drifting across the detector. In practice, Gaia might have 500,000 stars on the detector at any given time, and thousands of stars are having their brightness and their times recorded every second. And remember, that's effectively every second for 10 years. That gives you an idea of just the scale of the amount of data that Gaia produces. Gaia spins about once every 6 hours. The animations always make it look a lot faster than that. Remember, it takes about a minute for the starlight to cross the detector. Gaia spins once every 6 hours, and its spin axis precesses as it goes around the sun. That means the two telescopes map out a ribbon of sky, and that ribbon of sky sweeps across the whole sky as Gaia orbits the sun. The animation in the bottom right, the colours represent how often that chunk of sky has been reached by Gaia. And you see that various parts of the sky are mapped out multiple times. Not necessarily exactly the same amount for every point on the sky, but every point on the sky is mapped out multiple times during Gaia's lifetime. So what data was what data was acquired? The original mission, starting in 2014, was then followed by the extended mission, giving us a little over 10 years of data acquisition, about 10.5 years in total. And data was released in a whole load of batches, 7 batches. You might think that those would be numbered 1 to 7. No. 1, 2, E, 3, F, 4, and 5 were the data releases. You can see the first data release was not immediately after the start of the mission. It takes a while to collect data, and it takes a while to analyze that data. Remember, the raw data of Gaia is timings and brightnesses and colors and spectra. If we want to convert those timings to the accurate position, we have to think about how Gaia is spinning and make a model of where we think those billion stars are, and then try and match that up to all of the timings we have. The first data release, which took the first 1 year of data, produced coordinates for maybe a few million stars. Data release 2, a couple of years later, gave us 2 years worth of data being processed to give us the coordinates of billions of stars. Scientists were getting antsy for data release 3, so there was an early release, as indicated by release E, which gave improved precision by taking 3 years of data. I hope it's obvious that the more data you take, the more repeated measurements you take of a star's position, the more accurately you can determine what it's doing, both in terms of its proper motion and in terms of measuring the parallax and hence the distance. So the more data you're putting into your model, into your analysis, the greater the precision achieved. Data release 3 in 2022 produced billions of stars to very high precision, but in addition, it also produced data on millions of variable stars, because remember, the brightness of the stars, not only their positions, are being measured, and so we can look at trends of variations of intensity. So we've now got data on millions of variable stars. By accident, we've picked up a few million galaxies, which look a little bit like stars when they are small. And that's actually quite useful because some of these galaxies are very remote. The brighter ones are quasars, which might be billions of light years away. They are so remote, they have essentially 0 parallax and 0 proper motion. And therefore they act like the fixed stars that we don't have in the Milky Way. All of the objects in the Milky Way are in motion, but we can treat very distant quasars as being fixed points in the sky. So now we are able to measure the actual coordinates of stars relative to a fixed coordinate system. By accident, we've also picked up perhaps 100,000 solar system objects, a lot of them asteroids. Some of them we already knew about, some of them we didn't. In 2024, there was a focused product release. That took the first 5 years of data. As well as trying to give us high precision on billions of stars, it also looked at how can we make the analysis even better. They looked at a very crowded region of the sky, the Omega Centauri globular cluster. From even the best measurements we can make, for instance, a view like this from a Hubble Space Telescope, there's an awful lot going on and there's a very crowded field towards the center of globular clusters. Even a telescope like the Hubble can't resolve all the stars in there. The analysis was carried out for the very dense region around Omega Centauri, and Gaia found perhaps 500,000 stars that Hubble wasn't able to resolve. The idea is if we can make the analysis even better by using Omega Centauri as a touchstone, then it should be possible to use that refined analysis to go back and look at the very dense regions, for instance, close to the center of the galaxy. Data release 4 will be later on this year. I think it's currently slated for somewhere around December 2026. That will be a huge data release, and the final data release will be probably 2030 or so, data release 5, which will include everything, the full 10 years of data with the maximum precision possible. Let's think about what it is that we've learnt about the Milky Way. This is what we think the Milky Way looks like based on Gaia data so far. We have a number of spiral arms. It looks like the Sun is in the Orion arm. It used to be the Orion spur. It appears to have got a promotion. Now it appears to be an arm in its own right. The yellow dot on the left and the right tells us where the Sun is relative to the centre of the galaxy. About 8,000 parsecs, or if you prefer, about 25,000 light years from the centre. If we think about what Hipparchus told us, remember Hipparchus only looked to magnitude 12 and only looked at something like 100,000 stars. So all of the stars that Hipparchus could see were all relatively close. They were all inside that yellow dot. Gaia has been able to extend that range. Gaia data release 2 in 2018 made that dot a little bit smaller, but still, of course, it's only our local area, our local spiral arm. Data release 3 with much higher precision allowed us to get measurements of stars at much greater distances. And data release 3 pushed that boundary of what we've been able to study in the Milky Way way beyond what was previously possible. Data release 3 allowed us to look at stars out to those sorts of distances. That doesn't mean we've mapped every star out to those distances, but some of the brighter ones we've seen out towards the edge of that green circle. The centre of the galaxy is still too dense for us to get a lot of data, but we are now getting a good indication of what a lot of stars in the Milky Way are doing in terms of their distances, the three-dimensional structure, and their motion. If ever you see a picture like that, it's tempting to think that that's an image taken by Gaia. But it isn't actually an image, it's a map, where each pixel in this particular map isn't telling you about there's a star in that direction. It's really telling you how many stars are there in that direction. The brightness of the pixel is simply how many stars did Gaia see in that tiny chunk of sky. And because there are so many stars towards the centre of the galaxy, not surprisingly, it looks a little bit like an image would if you took an image of the Milky Way as seen from the inside. And again, you see a lot of stars in the Magellanic Clouds in the bottom right. But technically it's not an image, it's a plot of how many stars did Gaia find. What can we learn from the data that's coming out in these data releases? Well, one thing we now know is about the stars themselves. Remember, now that we can measure the distances to a lot of stars, we can get their luminosity, which means instead of guessing what a Hertzsprung-Russell diagram might look like for our Milky Way, we now have enough data that we can say this is actually what the HR diagram looks like. Each dot is not a guess. Each dot is data from a star. And in the middle there are so many stars we've had to change to a colour map from red to yellow, telling us how many dots there are in each of those pixels. So now we have an accurate indication of what the population of our galaxy looks like, at least in a relatively large fraction of the galaxy on this side of the galactic bulge. So we can now test our ideas of stellar evolution based on this real data. A few things were not really expected. For instance, we actually found quite a few sun-like stars, stars very similar to our star in terms of its size, its mass, its age. But some of these stars are orbiting something that is quite massive but invisible. And it's been deduced that it's not massive enough to be a black hole, but it's of such low luminosity, then perhaps it's a neutron star. Massive, but not very bright. So it looks like we've got 20 or so candidates, not many compared to the billions of stars that have been measured, but a large enough number to say that, well, this happens. Somehow, sun-like stars can survive a neutron star being formed. But we thought that neutron stars are born in supernova. How can a sun-like star survive orbiting an object which goes supernova? We need to understand these systems better, because there's clearly something we still don't understand going on here. We've come to the conclusion that the Milky Way galaxy is warped. Here's an artist's impression, as it were, of what it might look like if we were to step out of the Milky Way and look at it from a distance. The disk of the galaxy is not dead flat. We've known this about other galaxies. Here's a galaxy, for instance. If you look very carefully at the dust laying down the centre, it's not directly down the centre of the galaxy. It's slightly higher on one side and slightly lower on the other, indicating it's got a warped disk. And we suspected that the Milky Way might be similar to that. Now we have the data that tells us it is. A warped disk is almost certainly the result of galaxies interacting with our own. If we look at stellar motion, here each dot is a star, and the lines indicate how those stars are moving. Remember, once we've separated parallax from motion, parallax gives us distance, and the motion allows us to see how the stars are moving around the Milky Way relative to the centre of the solar system. Using all of that information, we can get an idea about star orbits. A lot of stars are going around the centre of the Milky Way in much the same way that we would expect for 99% of the stars. But there are a significant number of stars which do not appear to be orbiting the way we would expect. Some are going backwards. Some are going over the poles. Some are in extremely elliptical orbits rather than a well-behaved circular orbit keeping roughly the same distance from the centre of the galaxy. So, taking these stars with peculiar orbits, we can effectively backtrack and say what must have happened in the past in order to give stars like these such peculiar orbits. And we've come to the conclusion that the Milky Way has merged with other galaxies in the past. We've assumed that was the case by looking at other galaxies out there in the universe. We've always assumed that the Milky Way is the result of galaxy mergers. Now we have evidence that tell us this is indeed the case. And we can get timings down reasonably precise. This map tells us about galaxy mergers that have happened, and the timescale on the top gives us billions of years since the Big Bang. The timescale on the bottom is the same thing backwards, the time before the present. And each of these galaxy mergers we can pin down with reasonable precision. I'm not going to talk through all of these, but there are reasons to believe, for instance, that the galaxy here that I've labelled Enceladus, it looks like, when we look at the globular clusters that we see in our Milky Way, it appears that some of them have been stolen from other galaxies. We think the Enceladus galaxy actually merged with the Milky Way 3, 4, 5, 6 billion years, 3, 4, 5, 6 billion years after the Big Bang, or about 8, 9, 10 billion years ago. That galaxy merged with ours, and effectively we have incorporated its globular clusters into the Milky Way. We've deduced that from the way things are moving, as well as their chemical composition being somewhat different from other globular clusters in the Milky Way. If we have a look at the one on the top right there, the Sagittarius dwarf galaxy, that's a rather interesting situation. I'm just going to call it Sagittarius from now on, just for brevity. This is what we think has happened. The Sagittarius galaxy clipped the Milky Way about 6 billion years ago, and then it's got disrupted and produced a star stream, and then it sort of came back and clipped the Milky Way again about 2 billion years ago. and continued on and clipped the Milky Way a third time about 1 billion years ago. Each time Sagittarius clipped our Milky Way, there was fresh star formation. And effectively, the Sagittarius galaxy has been stretched out into these either tidal tails, or if you prefer, these star streams. It's effectively a breadcrumb trail that tells us how Sagittarius has behaved and how it's interacted with the Milky Way. And it's rather interesting to note that the evidence we have about Sagittarius, in particular the interaction of about 6 billion years ago, which certainly would have produced a whole load of new star formation, that coincides roughly with when our sun was born. In other words, our sun was born shortly after the Sagittarius dwarf galaxy interacted and clipped the Milky Way, and the gravitational disruption would have produced new stars. So perhaps, a little bit of speculation, perhaps the sun and we are the result of an interaction between a small galaxy and the Milky Way some 5 or 6 billion years ago. This idea of star streams, again, we've seen it in other galaxies. We suspected that they were there in the Milky Way. Now we know they are. The star streams are visible in this particular galaxy. If I change the contrast, then you can see those star streams even more dramatically, again showing us a breadcrumb trail of how galaxies have interacted with this one. M63 perhaps looks like a galaxy relatively isolated, but if we do the same trick and bump the contrast up, you can see there are quite definitely star streams surrounding M63, again indicating that M63 has interacted and possibly cannibalized other smaller galaxies. The more we look, the more we see. Here again, we change the contrast. Not so obvious in terms of a star stream, but definitely indications of interactions in the past. The more we look, the more we see. Now we have direct evidence that this is not something that only happens to other galaxies. This is something that has happened to the Milky Way. Not only can we use the motion of stars to say this must be what has happened in the past to explain why we have the motions we have now, we can also to some extent talk about what's going to happen in the future. We can extend the graph off to the right. The Sagittarius dwarf galaxy is apparently still interacting with us, though we're not entirely sure what's going to happen in the future. And we know that there are going to be 2 interactions in the not so distant future, about 2 to 3 and possibly 4 to 5 billion years into the future. The first will be an interaction with the Large Magellanic Cloud, and the second will be an interaction with the Andromeda galaxy M31. I find it quite incredible that these are galaxies outside our own, and yet it is possible for Gaia to use the idea of parallax, which hopefully should work for stars tens or hundreds or thousands of light years away, but actually Gaia has sufficient precision that it's actually able to measure the parallax of stars in other galaxies. And it is hoped that the precision with which we can measure the parallax of stars in the Andromeda galaxy, when data release 5 comes along, there'll be enough data to give us the precision to be able to tell precisely what's going to happen with the projected impact between M31 and our own Milky Way. Is it going to be a head-on collision? Is it going to be a glancing blow? Data release 5 might resolve that question. So let me finish with a little epilogue. The data acquisition phase of Gaia finished in January 2025, a year and a half ago, at which point it was then put into a retirement orbit. Sounds so much better than a graveyard orbit, doesn't it? With objects orbiting around L2, if you simply nudge them a little bit further away from L2 so that they are outside Earth's influence, they will drift away and continue orbiting around the Sun, but no longer stay at the L2 point. This ultimately will happen with any satellite. In the case of James Webb, for instance, it's being kept this side, the Earth side of L2, very carefully, because we do not want to let it drift beyond L2, at which point we will effectively lose it. With Gaia, it was deliberately nudged away from L2 to make more space for any other space satellites, space telescopes that we would like to place in halo orbits around L2. As it drifted away from L2, some people managed to photograph it. This S here is Gaia moving away from L2. It's moving around the Sun at a different speed to the Earth, and perhaps in 14 years or so it'll get a little bit closer to the Earth. It'll never come back to L2, but it will get close enough and it might be possible to pick it up again. Before it was powered down completely, Gaia sent its final message back to Earth, which the controllers engineered with data such that it would spell out a little goodbye message. Will there ever be another Gaia? Is there a Gaia Mark II waiting in the wings? Well, not really. Any idea of having a higher precision version of Gaia will be well into the 2030s and possibly into the 2040s before any such mission is contemplated. Coming up fairly soon is the Nancy Grace Roman Space Telescope. That has got a very large detector. It's going to have the same precision in terms of how much detail it can see as the Hubble Space Telescope, but there's the field of view of the Hubble Space Telescope compared to the field of view of the Nancy Grace Roman. You can see that the field of view is 100 times higher with the same detailed precision. Now, Nancy Grace Roman will be an infrared telescope, so it will be able to see regions that Gaia finds difficult, the very crowded, the very dusty regions towards the centre of the galaxy. Nancy Grace Roman will hopefully be able to see more detail than Gaia can. But Nancy Grace Roman is not tasked with reproducing the Gaia catalogue. It might end up producing parallax of some stars towards the centre of the galaxy simply because it's better suited at doing that. But it won't be mapping out the parallax of billions of stars. So Gaia has been producing huge amounts of data. The next data release 4, later this year, is estimated at something like 500 terabytes of data. That's star brightnesses, star positions to phenomenal accuracy, the proper motion, the distances, as well as the colours of the stars, and for some of those stars, the spectra of the stars. So astronomers will be going through this data. Of course, they'll be using AI tools to help sift through these hundreds of terabytes of data so that they can hopefully produce a better understanding of the three-dimensional structure, the three-dimensional dynamics and evolution of the Milky Way, the evolution in the past and how it's merged with other galaxies, as well as what's in store in terms of merging with the Large Magellanic Cloud and the Andromeda Galaxy. Some of this huge amount of data is in star characteristics, the colours of the stars, the brightness of the stars, effectively all of the information we can then deduce from that, such as the age and the composition of the stars. And so we'll have data on hundreds of millions of stars, which will enable us to get much better handle on our models of stellar evolution. Sifting through all this data, we'll also find more neutron stars. Gaia has already found one of the largest black holes in the galaxy that isn't actually sitting at the centre. And it's found solar system objects, and it's by accident found some exoplanets because it's got such high precision of looking at how stars move. After you take out parallax and after you take out proper motion, if you're left with a little bit of a wobble, that indicates that you've got an exoplanet going around the star. Data release 5, when it comes along in a few years' time, will be even higher precision. And if we've got high precision on many billions of stars' motion, then it might be possible to get an even better handle on how dark matter and ultimately dark energy are distributed throughout our galaxy. Gaia can be summed up in two words: obscurity and ubiquity. Obscurity because it's nowhere near as famous as its very famous cousins, the Hubble Space Telescope and the James Webb Space Telescope. But ubiquity because Gaia data is everywhere. Gaia data is being used by every ground-based telescope, every space-based telescope, every astrophysics project for the next 10 or 20 or more years will use Gaia data. Gaia data is Gaia's legacy. Thank you for listening.